Howdy, howdy, this is Mr. Potter. Today we're going to be talking about roots of unity and DeMoivre's theorem. So I want to start with a very simple equation that we see a lot in our Algebra 1 question. We have x squared equals 1. Now I know that this is a parabola, so if I was to graph this, then I would see a parabola. And the idea is that if I have the line y equals 1, I know this is going to intersect at 2 points. It's going to intersect at the point 1, 1, and it's going to intersect at the point negative 1, 1, which means that we have two solutions. We have x equals 1, and we have x equals negative 1. And of course this makes sense because it's a second degree polynomial, so we should have two solutions. We have x equals 1 and we have x equals negative 1. If I were to continue this idea and take a look at x to the fourth, what I've really got here is a quartic. But we know that a quartic equation looks a lot like a quadratic equation, it's just narrower. And one of the things that we notice is that if we graph this and draw the line y equals 1, we're going to see that it's going to intersect at the point 1, 1, and it's going to intersect at the point negative 1, 1. And so it appears that x equals 1 and x equals negative 1 are our only two solutions that we have here. But also keep in mind that we do have another property when we've dealt with x to the fourth. It's the idea that I, which we've defined to be the square root of negative 1, has this kind of periodicity. We have I squared, I cubed, and I to the fourth. I know that I squared is negative 1. We know that I cubed is negative I, and I to the fourth is 1. Well, this looks suspiciously like x to the fourth equals 1. The only difference is instead of having a variable x, we're dealing with our imaginary constant I. But if I were to take a look at I and raise it to the fourth power, of course that's going to give us 1. I squared raised to the fourth power, well, that's really negative 1 to the fourth power, which is 1. If I take a look at I cubed and raise it to the fourth power, then what I'm really doing is I'm taking negative I and raising it to the fourth power. But keep in mind that negative I times negative I times negative I times negative I, well, negative I times negative I is going to give me negative times negative is positive, I times I is positive negative 1. And negative 1 times negative 1 does give me the positive 1. And of course, if I take I to the fourth and raise it to the fourth, then that's really 1 to the fourth, which is 1. So what I really have is I do have four solutions. I know that x equals I is a solution of this equation. And I know that x equals negative I. X equals, horrible, horrible, ugly, ugly, bad, 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 bad. X equals negative I is also a solution to this equation. And so what we notice is that we have a fourth degree equation with four solutions. A second degree equation has two solutions. And this actually leads us to the idea of the fundamental theorem of algebra. Now we normally see the fundamental theorem of algebra being written as x to the n has, at most, in real, x to the n equals k has at most n real solutions. But in reality, what we have is that x to the n equals k has n complex solutions. In reality, what happens here is that even though I can't necessarily think of real solutions, enough real solutions to satisfy. So for example, in the x squared case, of course, there's positive 1 and negative 1, but in the x to the fourth case, 1 and negative 1 were the only real solutions, but we do have two additional complex solutions, and these complex solutions happen to be complex conjugates of each other. We do have the ability to come up with exactly four solutions, which of course, x squared, okay, that's pretty easy. X to the fourth, that's pretty easy. What about x cubed? Well, if I was to take a look at x cubed equals 1, then of course, x cubed equals 1, then x equals 1, and something, and something. The question is, how do I figure out these somethings? And if I want to figure this out, then I really need to go back and revisit the two things that we've seen so far. When I was dealing with x squared equals 1, we had two solutions, x equals 1 and x equals negative 1. But if I was to go ahead and graph those on the real imaginary plane, I'm going to see I'm going to have one solution here and one solution here. If I take a look at x to the fourth equals 1, then of course I've got x equals 1, x equals negative 1, x equals I, and x equals negative I. But again, graphing those on the real imaginary plane, I'm going to notice that they're going to be 1 and negative 1 and I. Remember, I is the imaginary plane, so it's basically our y-axis, and negative I. And one of the things that I notice is that if I were to consider a unit circle, horribly graphed circle, but you know what I'm talking about here, then to get from this point to this point, this is really a 180-degree rotation to get from here to here, and similarly 180 degrees to get from here to here. If I consider my unit circle for x to the fourth, then of course to get from this solution to this solution is 90 degrees, 90 degrees, 90 degrees, and 90 degrees. Which means I have this conjecture, maybe, just maybe, if I take a look at my unit circle, and I know that I have a solution here at x equals 1. I know that's one of my solutions for x cubed equals 1. But if I were to divide my unit circle into 3 equal angles, well, I'm going to have one angle that's going to exist out here, about 120 degrees rotated counterclockwise from the positive x-axis. And then if I continue another 120 degrees, I'm going to end up over here. And then if I continue another 120 degrees, then I'm going to end up over here. So this brings up some interesting ideas that maybe this point, which is 120 degrees away from the positive x-axis, this may be a solution. Let's call it x sub 2, or if this is x sub 1. And this could be another solution. This could be x sub 3, this thing that's really 240 degrees away from the positive x-axis. So the question is, could I actually get these to be roots of unity for me? So let's take a look at this. Let's consider this. Let's test it out. So the idea here is that, of course, remember that x is going to be equal to r cosine theta and y equals r sine theta. So for us, our theta is 120 degrees, or 2 pi over 3 radians. Same angle that we're talking about. So I'm actually going to let omega 1, this is going to be my first root of unity that I'm going to call it. Actually, let me call it omega 3 because it's a third degree polynomial. Omega 3 is going to be equal to 1 times the cosine of 120 plus I times the sine of 120 degrees, which for me, cosine of 120 is negative 1/2. And the sine of 120 degrees is going to be positive root 3 over 2. So I'm saying this could be a solution to x cubed equals 1. Well, let's check it. So I want to take this and multiply it times itself, then multiply it times itself again. And my question is this in fact equal to 1? Well, let's do some distributive property here. So negative 1/2 times negative 1/2 is going to be a positive 1/4. I root 3 over 2 times negative 1/2 is going to be negative I root 3 over 4. Negative 1/2 times I root 3 over 2 is still negative I root 3 over 4. And then I root 3 over 2 plus I root 3 over 2 is going to be negative, because I times I is negative 1, 3 over 4. So what I end up with is negative 1/2 plus, excuse me, not plus, minus, this is going to be root 3 over 2. And this is the result of these two things being multiplied. I still have to multiply this result times negative 1/2 plus I root 3 over 2. And one of the things I notice now is that these are complex conjugates of each other. It's very interesting. We're going to touch upon that in just a moment. Multiplying this out, negative 1/2 times negative 1/2 is a positive 1/4. Negative root 3 over 2 with an I times negative 1/2 is going to be a positive I root 3 over 4. This I root 3 over 2 times negative 1/2 is going to be minus I root 3 over 4, and that's certainly nice. And then negative times a positive is negative. I times I is a negative, so that's just going to give me plus 3/4. And 1/4 plus 3/4 is 1. So this checks. This omega that we've got here, this negative 1/2 plus I root 3 over 2, when I cube it, I do get 1. So that means that this is what we would call a root of unity, because cubing it gets me 1. Now keep in mind, that's this point here. Interesting enough, this point here, that's at 240 degrees. So if I consider that, if I call this omega 3 prime, which I'm going to call 1 times the cosine of 240 degrees plus I times the sine of 240 degrees, well, this is just negative 1/2 again. It's third quadrant, so it's the same as the second quadrant for cosine. The main difference here is third quadrant sine and cosine are both negative, so this ends up being negative I root 3 over 2. And my goodness, this does look familiar. And what I can find out without really any loss of generality is that if I were to cube this value, I also get 1. So revisiting what I've got, if I have x cubed equals 1, then of course I could say x equals 1, or x equals negative 1/2 plus I root 3 over 2, or x equals negative 1/2 minus I root 3 over 2. Notice that it's a third degree polynomial. I've got 3 solutions here. It's really convenient. Can we generalize this though? Well, we can generalize this if we talk about CIS notation. Now, if you haven't seen CIS notation before, this is a way of expressing complex numbers as cosine of theta plus I times the sine of theta. And I want to talk about where this actually comes from. So in our calculus class, we know that we can write e to the x as an infinite geometric series, as n goes from 0 to infinity of x to the n over n factorial. And what that means is that I could write e to the I times x as the sum from n equals 0 to infinity of ix raised to the nth power over n factorial. So if I was to write the first few terms of this out, of course, anything to the 0 power is going to be 1, and 0 factorial is 1. If I substitute n equals 1, then this is going to be I times x over 1 factorial, which is 1. Then if I take square, I squared is going to be a negative 1 x squared over 2 factorial. I cubed is negative I x cubed over 3 factorial. And this pattern is going to continue 1x to the 4th over 4 factorial, I x to the 5th over 5 factorial, minus 1x to the 6th over 6 factorial, minus ix to the 7 over 7 factorial, and of course this continues forever. What's important for me though is that I really have 2 different types of expressions here. I have my real expressions, which I can write over here as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus da 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 da. And I've got my imaginary terms here, 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 here. My odd terms end up being imaginary because they're odd powers of pi. So I've got I times this, really x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus da 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 da. This is going to continue over. So what I've got here is I've got two different terms here. One term, which is my even powers. And these even powers really is the formula cosine of x. This is the power series expansion for cosine of x, and we learned this in our calculus class. Over here for these odd powers really are our polynomial expansion for sine of x. And so what we've got here is that this e to the ix is really equal to cosine of x plus I times the sine of x. And we'll often see this written as e to the I theta equals cosine of theta plus I times the sine of theta. And so this is just another way that we can write complex numbers. We can write complex numbers as a plus bi. We can write complex numbers as cis of some angle theta, or we can write them as e to the I times theta, where all of these are going to be points on our unit circle. Great. So how does this help us with this powers that we're talking about, this roots of unity, being able to solve these equations where a polynomial term equals 1? Well, we can use what's called DeMoivre's theorem. The idea, of course, is that if I have something like x cubed equals 1, well, I know that my solution is going to be some form of e to the I times theta. And I also know that because this is cosine of theta plus I times the sine of theta, if I want this to be 0 and I want this to be 1, because this needs to be equal to 1, I really need theta to be the right x-axis terminus of my unit circle. So in other words, theta is going to have to be 0 or 2 pi or 4 pi or something that's coterminal with those values. So let's see, if I let x cubed being equal to e to the I times 0, or x cubed equals e to the I times 2 pi, or x cubed equals e to the I times 4 pi. Well, if I want to get rid of this power, I can take x cubed and raise it to the 1/3 power. Because these powers are reciprocals of each other, they will cancel out. But if I do it to one side of my equation, I need to do it to the other side. So it's going to have to be e to the I theta to the 1/3 power. Well, theta here is 0. And 1/3 of 0 is 0. And we already know that e to the I times 0 is going to be just 1. And we know x equals 1 is our trivial solution to these polynomial equations. Over here, this is a little bit more complex, though. If I have e cubed to the 1/3 power, this is going to be e to the I times 2 pi raised to the 1/3 power, or e to the I times 2 pi over 3. So this is going to mean that x is equal to the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3, which we've already seen before as the 1/2 plus I times 3 over 2. And we know that this was our omega that we were talking about earlier, this omega 3, this third root of unity. And then if I do the same thing with 4 pi, if I raise both of these to the 1/3 power, that's going to be 4 pi over 3 when I do that over here. And so x ends up being the cosine of 4 pi over 3 plus I times the sine of 4 pi over 3, or negative 1/2 minus I root 3 over 2. And so DeMoivre's theorem basically says that if I can write 1 as e to the I times 2 pi k, then my root of unity is going to be e to the I times 2 pi k over n. In other words, if I want to solve x to the n equals 1, n is going to be what I'm dividing by, because I'm basically multiplying the exponent by a reciprocal, a 1/3. And I need to do that for all values of k from 0, 1, all the way up to n minus 1. And that's going to give me my n roots of unity. So this really does help quite a bit. Now we've already explored what's happening here for x cubed equals 1, so let's take a look at something like x to the 6th equals 1, which of course I know I should have 6 solutions. And I already know that x equals 1 and x equals negative 1 are going to be 2 of those solutions. Because it's even, that makes this really easy to figure out. So the question is, what are my other 4? Well, I know that I want to take x to the 0 or x to the, e to the 0 or e to the I times 2 pi or e to the I times 4 pi. I want to take these multiples of 2 pi all the way up to 1 less than 6. So 5 times 2 pi is 10 pi. And I want to take each of these and I want to raise them to the 1/6 power. Now this, of course, is just going to be 0. That's where we get the 1 from. And e to the I times 6 pi, well, 6 pi divided by 3, or 6 pi, excuse me, divided by 6 is going to give me just pi. That's going to give me the negative 1. The tricky one is what happens at 2 pi and at 4 pi, because those do not give me a full multiple of pi. They give me a partial multiple of pi. This is going to give me e to the I times pi over 3. And of course, pi over 3, that's going to be cosine of pi over 3 plus I times the sine of pi over 3, which ends up being, 1/2 plus I root 3 over 2. So this is going to be one of my roots of unity, and its complex conjugate is going to be the one that's just as far away from this. So from 2 pi to 10 pi, well, those are on either sides of 0. So the complex conjugate is 1/2 minus I root 3 over 2. This is going to be another one of my roots of unity. So I could think of this as omega 6. Similarly, I can do the same thing with 4 pi. So it's going to be e to the I times 4 pi over 3, which is going to be, not 4 pi over 3, 4 pi over 6, which is 2 pi over 3. So it's going to be cosine of 2 pi over 3 plus I times the sine of 2 pi over 3, which ends up being negative 1/2 plus I root 3 over 2. And of course, if that looks familiar, well, x cubed squared will give me x to the 6th. So all of the roots of unity for x cubed should also be roots of unity for x to the 6th. This is our omega 3 that we were talking about. If this value is omega 6 prime, then this conjugate for this, negative 1/2 plus I root 3 over 2, would really be omega 3 prime. And if I really wanted to, I could think of this as omega 2, because this is really the complex conjugate, or not the really complex conjugate, but this is really the root of unity for our x squared. So what's interesting to note is that all of our roots of unity are going to be sharing a factor with the roots of unity that came before it. A 6th degree would have to share the roots of unity of the 3rd degree and the 2nd degree polynomial, because 2 and 3 are factors of 6. And their complex conjugates would also have to be roots as well. This brings some really interesting ideas of how to deal with these equations that normally we think are very simple. And realizing that this equation has 7 solutions instead of just 1 solution, instead of just the trivial solution, is really interesting. Once again, this is Mr. Potter. Thank you for watching. Have a great day.